Come to grad school, PhD. I could teach you incredible things. Systems.
Well, he said to thumbs up when done, please. So I think maybe he just didn't see the thumbs
Systems, graphics, PL, Sin. Saw your transcript and I thought, oh my God, look at those grades.
I think we can starting. Ranjit is there. Someone made you a password in the chat. You can just use that. No one's gonna hack into your account, don't worry. But yeah, hi everyone. Thanks for coming. This is a really exciting day. It's a really exciting back-to-back on PL Talk because last week we talked about Ranjit's paper and this week we have Ranjit himself. It's even better than the time we talked about Jeremy Seek's paper and Jeremy just emerged on the chat. This time we had a whole week to digest. It's incredible. So for everyone who doesn't know what PL Talk is, our goal, it started out with me and Hongi discussing one paper and deciding to make programming languages more accessible to the world, because it's our hypothesis that if everyone just knew how cool programming languages was, everyone would be obsessed with it too. So far that hasn't panned out, but I think we're getting there. A little bit about me. I'm the founder and CEO of a company called Akita Software. Oh yeah, we're hiring some senior engineers. If you are one, you should come work with us. Everybody else can introduce themselves very shortly, but I'll just quickly introduce today's topic so I can get all my talking done in one chunk. So we have Ranjit Jhala, the esteemed Ranjit himself. He is a professor at UC San Diego. I remember he is such a good speaker that when I was a grad student, I would watch him give talks and I would be like, this is not fair. He's just so good. So Ranjit is very, very good speaker. He created this kind of refinement type checking called Liquid Types, which I think is the most accessible developer experience friendly type checking for refinement types out there. So today we have Ranjit himself to talk about that, what it feels like to be a pop sensation, how he became so cool, and many other topics that you can feel free to propose them in the chat. But yeah, Hongi can introduce himself quickly and then Ranjit can take it from there.
Sure. Yep, I'm Hongi Hu, a PL enthusiast, I guess I would say, currently doing security engineering at Figma.
And then, yeah, Ranjit, you can tell everyone about yourself, your hopes and dreams for today, everything.
Oh, for today, well, I just hope to get 10 hours of sleep today. Sorry, let me just say a few things about myself. I'm Ranjit. Jean already said I'm a professor at UCSD. I've been talked by my colleagues into making these very embarrassing videos, but you know what? I've just grown to love and have embraced them. I'm very glad we've now hired Nadia, who I think was on PL Talk a few weeks ago, right?
Yeah, she's one of our first guests.
And who can actually sing and play music, and it's just fantastic. And so I've kind of handed off the baton a little bit on that. My hopes for today. No, I was going to just say my hope for every day is to just get between 8 and 10 hours of sleep. And
that's
I'm just
incredible. I only get that much sleep once a week.
I have one word for you, Jean. Tenure, baby. Tenure. That's what it is. But you need anyway. I'm always reminded of your tweet, which I hadn't realized it had gone quite so viral. Like maybe your most viral. This is the one about when you think everyone in the world hates you, you need to eat. And it is so true. It's so true. I've never heard it put so well. I keep telling myself that as well. Anyway, that's my hope for myself every day.
That's great. We should all go around and say our hopes
That's a good aspiration.
Yeah, everybody in the chat, please say your hopes for yourself too. This is very interesting and illuminating. Maybe we can learn from everybody. But yeah, I think that I'd love to just start out by having Ranjit give us a quick tour of how did you come to work on refinement types and programming languages and security. If it's not an interesting story, we can actually skip it. But I think people out there are probably very curious.
Let's see. So let's see. I guess refinement. I honestly don't know. I always tell people this, that the great thing about PL is that nobody can fake interest in it. It's one of those things where, the contrast that I would draw is with something like, say, like machine learning or graphics. Everybody thinks that stuff is cool, but with PL, if you think it's cool, nobody fakes it. You really, there's something strange about it. So I guess I just had a really kind of, I probably had a really influential undergrad advisor, and I learned about the lambda calculus and all that kind of stuff. And I just got drawn into it. And all at the time, even my classmates where I was an undergrad were like, what is wrong with you? This stuff is like the most boring thing on the planet. I don't like, what do you like in this? But, I mean, I don't have to tell. If you're at PL Talk, you probably know some of this because you're kind of, you've seen some of this yourself. But yeah, I just got drawn into it. But the refinement type story is a little more involved. I guess back in grad school, I worked on something called software model checking. So I built, my friend Rupak Majumdar and I and various other people, we
Love
built a software
Rupak.
model. What's that?
Greatest. Love Rupak, the greatest
Yeah,
guy.
Rupak is just fantastic. So he was my office mate, and we worked on a thing called Blast, which is anyway, long story short, it was a kind of an analyzer for C programs. And we wrote the papers and we sort of built the tool, and we were working in OCaml, which is the language that I love OCaml. I love ML, like ML family languages. So again, I saw this thanks to I think a lot of this just goes back to having like really inspiring teachers at kind of pivotal moments. Like I had a really good high school teacher actually who really got me into computing in the first place. And he was an interesting guy because he would teach computer science and he would also teach theater. That was his thing. And I don't know how these two, but he was like an award-winning player. And he was amazing. So
Nice.
it was
Yeah.
but he was just like really passionate. He really got me into it. And then I had these really great undergrad profs and so on, who got us into functional programming. So anyway, we were working on we were using functional programming, OCaml, to write these model checkers, which were supposed to analyze C programs, right? So that's what I did. I had a great time doing it. But it was very frustrating because, and we sort of made it work for like C device drivers and things like that, but we could never figure out how to deal with things like data structures, like lists and hash tables. And I mean, just basic things. These are just really basic things. And in theory, so model checking, for those of you who don't know about it, it's sort of emerged as a kind of method for analyzing kind of finite state machines, finite state sort of communication protocols, hardware circuits. That's where it really had a lot of kind of impact. Gene's sort of former colleague at the Carnegie Mellon, Ed Clark, got a Turing Award. It was like a big deal, but it had its roots in this kind of finite state world. And so to make it work for C required a fair bit of kind of, thought. But still, we couldn't make it work for real software because we're like lists and trees and hash tables. And when I was in grad school, I didn't know a thing about type systems other than, just what a regular sort of ordinary programmer knows about type systems. I certainly don't know about refinement types, any of that stuff. But we were having lunch. We had this kind of group lunch, and one of the other professors there, a gentleman called Alex Aiken, he made this kind of offhanded remark saying, "Oh, people struggle so much with this stuff. The functional programming people and the types people, they figured all this out." I'm like, really? What is this magic thing that they figured out? And this was, when I was, I don't know, maybe 2000 or something, 2001. And that's when I kind of, what's this? What is this type system? And why do they have it figured out? And yeah, kind of, that's how I got into it. So I was like, all these problems, trying to understand how to reason about data structures and lists, just basic things that every programmer, like, we teach sort of first year undergraduates to do that kind of stuff, right? But to try and get a machine to understand that in your code was so difficult that we were making up new logics and shape analysis and so on. So anyway, that's how that particular quest began. And then I looked at all these, there were various papers coming out. And essentially, the way I got into refinement types was, how do you take these ideas from model checking and how do you get them to work with type systems? So I can tell you more about what do I mean by making these two things combine if you want. But I don't know, maybe I've spoken too much already and you'd rather talk about something else.
Well, we can take a quick poll of Hong Yi and the audience. What does everyone think?
No, I mean, I'm always interested in hearing the backgrounds just to get a better sense of like where, especially since I think a lot of problems in PL that at least we've discussed on this podcast don't quite make as much sense unless you like really understand what's going on or like sort of understand what kind of problems like people face earlier on in their career. So yeah, I think it's great.
So I'll tell you, okay, so I'll tell you a little bit more about how this kind of came about, right? So when you analyze a C program or any program, okay, here's what happens. I'll try and and this is the kind of analogy I had in my head. By the way, I should say this was like 15 years ago. And so I'm trying to reconstruct these analogies that I had in my head then. Is the problem we would have is I have, let's say it was let's say I'm a device driver, right? So it's a program, it's a C program that's a device driver, and it gets some information. You read some data from the sensor or whatever, and the number, and you're supposed to suck in, and it's supposed to be a number that's like whatever, an 8-bit integer between 0 and 255. Let's just say you get some kind of packet object like that, right? Some value. And then you take this little packet object and you stick it inside a data structure, okay? Inside a list or a hash table or a queue or who knows what, one of these things, right? Now what happens is, you can imagine this, the mental model you should have is, like a series of pipes or tubes where somebody somewhere at one point in your code, you sort of read this data and you put it inside this data structure. Like let's just say it was a hash table, right? I create this and I pop it inside the hash table. Now what happens is this data goes inside the hash table. And as you do all the thousands of hash table manipulations, maybe you insert other things into the hash table, maybe you delete other things from the hash table. Who knows, maybe it was a balanced tree, you rebalance the hash table. You're doing all kinds of weird pointer manipulations inside the hash table. And then maybe in another file entirely, or a long time or a long sort of space away, you pull the element out of the hash table. And what I want to know is I got back my 8-bit value, my number between 0 and 255. Okay. And the problem that we had with software model checkers and the way that entire kind of piece of technology worked is that you had to push that single bit of information that I have a number between 0 and 255. I had to push it step by step by step by step across each and every one of the low-level operations that the hash table did. I'm doing who knows what. Maybe I'm doing things not relevant to the hash table at all. I have like 4 different hash tables. But you have to somehow preserve that information if you want to get it out at the other end, right? And so who knows what Alex was thinking? He was halfway through a slice of pizza and he just made this offhanded remark about, I think the types people have figured this out. But I think what Alex was saying is, if you think about what happens inside a type system, again, to make this analogy, I like to think of it in terms of a transit, so I at the time I was like, what model checkers are really good at doing is they're like the little, what do you have those little scooters now? They're good to go from one place, to go from place A to place B, as long as it's really nearby. They're very precise. They'll tell you, oh, this data that you got in is a number between 0 and 255. So they're really good for this kind of super local, establishing this kind of local fact. But then if you want to take that information and propagate it way across your program, it's almost like, you then get onto the BART. You want to then put this piece of information on some form of mass transit, and you want to use this mass transit to kind of propagate it across your program, such that when you then get off at the other end, you get on the Caltrain station or whatever, right, in San Francisco, who knows what happened on the train, but when you get off at the other end in San Jose, it's that same, whatever I put in is what came out. I don't know what got put in, right? I'm just going to be, I put a thing in and I get a thing out. Okay, so the type system is really good for that kind of reasoning. So I think of types as really good as a form of mass transit, and model checking as really good as this kind of very fine-grained reasoning. But I don't want to, I don't want to ride a little scooter down the 280 or the 101 all the way to, from San Francisco to San Jose, right?
Yeah.
And so anyway, all of this refinement types was really trying to figure out, how do we make these two forms of, how do we make these two forms of transit work with each other? Because in types, you just say, you put an integer in and I get an integer out. But I don't want to just know that it's an integer. I want to know it was a special kind of integer that was between 0 and 255, or it was who knows what it was, right? But there was something special about that integer, and I want to get that information out. So anyway, that was really the kind of, that's what I wanted to do, right? I wanted, like, if only we can put these two things together, then we get this kind of the best way to reason about programs, where you kind of combine this kind of different kinds of transit.
Yeah, no, I think that's an awesome analogy. And I think it was, I had a similar opposite conversation with my group mate Rishabh when I was a grad student, because he was doing a lot of things with making model checking more accessible to modeling things. And I would make fun of him because I'd be like, functional programming has figured that out like 20 years ago. And it wasn't quite that, because there's exactly this tension that you described. But whenever I wanted to make fun of him, that's what I told him.
Right. Yes, you know what I mean. But lots of Lime scooters. Yes, that's what I was thinking of.
Yeah, cool. No, people are really resonating with your analogy.
Yeah, no, I think it makes a lot of sense. Yeah.
Cool. So do you want Ranjit to just give a quick overview of your journey through refinement types? Because you started working on it a while ago. You've had many iterations of it. Now you have this book that just came out yesterday. And you did it for Haskell, you did it for JavaScript. Do you want to just like walk people through like the arc of that?
Sure. I mean, I can give you my kind of, yeah. So I guess I've been working on this. I actually look back. I mean, technically, so it's a funny thing. This analogy that I made about mass transit, I wrote a grant proposal in like 2005, right after I graduated. I had no idea what a refinement type even was, but I knew I wanted to do this. And so I have all this kind of English description that describe the kind of stuff that I just told you about, but I had no idea how to actually, make the math work out. Um, but then I think around 2006 or 7, there were a bunch of other papers that started coming out that, so there were already, people in the type systems world were thinking about this, and well, they weren't thinking about this with this weird analogy that I have in mind, right? This mass transit. They were thinking of, as these kind of fancy type systems that let you do really cool things. So it turns out, I've been looking at the kind of the literature. Many of these ideas are there in like even the sort of late 70s, early 80s, certainly in the 90s. Various people in the kind of types and the functional programming world were thinking of these ideas. But they weren't really thinking with this kind of program analysis mass transit point of view. They weren't thinking of types as a form of mass transit. Is the way to think about it. But nevertheless, as I mentioned to Gene, I think one paper that really kind of, but I was a model checking person and I did not understand what these type papers were doing. I just could not wrap my head around the symbols. It's like, what is happening here? It's just really hard. And then Cormac Flanagan, who's at Santa Cruz, he's just an amazing person, by the way. He writes amazing papers.
Love Cormac, the best.
Just anyway, Cormac. But Cormac wrote this paper in like 2006 called Hybrid Type Checking. I think that's what it's called, which has a whole bunch of other stuff as well. There's the whole hybrid angle. But he was able to rephrase a lot of what the types people were doing in a way that kind of made sense to me. Like, oh, I see, that's what's happening. And my student, my first PhD student, Pat, who, by the way, I should, a random anecdote about Pat, which sort of connects with the thing I just said about you can't fake interest in programming languages. I remember when I was trying to recruit Pat to UCSD, I called him up on the phone and I said, actually, I didn't, sorry, no, that was somebody else. I didn't even have to call Pat on the phone because I just read his statement. People always ask me, what should I put in my statement? And I'll tell you what Pat had in his statement. The only thing I know about his PhD application is that it contained the following line. The Hindley-Milner type inference algorithm was my favorite thing that I learned in my 4 years as an undergrad. And this is the kind of line, if you put it inside your statement, I mean, you can't do it now because I just said it and this is now cheating, but I don't even know what his GPA was. I'm only dimly aware of where he went as an undergrad. I have certainly no idea what his GRE score was. That line was enough. I do not need to know anything else, because you simply cannot fake your interest in programming languages to this level. But anyway, Pat and I were kind of struggling with how do we make types work how do we make types work with Hindley-Milner, this, that, and the other. And then Cormac's paper came out, and then we had this idea where you can, this is where the first, what we call liquid types, this paper, we wrote this first paper, which shows how you can kind of connect types with this idea from model checking. So that was the first one. That was for OCaml in maybe 2008. And then I think we wanted to see whether you could make this work for C and JavaScript, imperative languages. And this was all in the pre-Rust era, right? 2008, 2009 is like before Rust, but I mean, Rust is really big now, but many of the core ideas in Rust is this notion of, ownership types, or where you're tracking aliasing inside your type system. And those ideas were already there in the kind of the research world. Gene has this nice analogy about how programming languages are like fashion, and it takes like 20 years for. So many of the kind of early ideas on which Rust were already there, and so much of that refinement type for sort of C and JavaScript, we were essentially trying to, look, if you just start using ownership types or these kind of type systems that track aliasing, then you can layer refinements on top of it, and that would give you kind of refinements not just for OCaml or functional languages, but for C or JavaScript. And so there was a lot of work to be done, but much of that work was essentially trying to develop a Rust-like type system for C or JavaScript. Once you could do that, the refinements were relatively easy. So anyway, we spent a bunch of time doing that. And then I have to tell you this. I think it's a funny story. Maybe it's not. I gave a talk at Microsoft Research. I visited Cambridge in the not the Massachusetts, but the the one across the Atlantic. And I gave a talk on some of this work, on the OCaml work. And Simon Peyton Jones, who is who's like one of the main Haskell people, um, he was in the audience and he's like, "Look, this is very cool, but I have to tell you something. If anybody is going to use this stuff, it'll be Haskell people. And so here's the deal. You should implement this for Haskell because that's how you know if it's a really good idea or not. If Haskell people it means it's
Great pitch, Simon Peyton Jones.
it works. He's like, look, if Haskell people don't use it, nobody else is going to use it. He's like, look, it's just because Haskell people, they're the only ones who really, I mean, if you really care about this kind
This is how Simon Peyton Jones tricks everyone into working on Haskell.
I know.
That's a great ploy.
This is what he did. I'm just telling you. It's just, I'm like, oh, good point. So I thought it was a pretty unique sales pitch. And so anyway, I got, and before I knew it, I was, I got pulled into kind of the I was about to say the rascal rabbit hole.
Yeah, because I was very curious how this happened, Ranjit, because you're like a C JavaScript guy before all this.
Yeah, and then I mean, so Simon, I think Simon has a lot to do with it. I was about to say, but Simon's like, look, and I mean, so it's a couple of things. The trouble with C, this is of course something I've with a lot of research, or I guess a lot of life, you kind of rationalize it after the fact. The catch with something like the catch with doing any of this work is I like to spend a lot of time programming myself. And I personally find it more fun to program in functional languages. And so I was like, look, if I am going to spend a lot of time, I just can't feel so vested, with JavaScript. It's too difficult, it doesn't give me enough joy working with it. So, but by the way, I mean, we did the C, and then Pat graduated, I guess. So Pat did all the C stuff, and it was very cool. But he graduated, as as PhD students, they do. So, and then Ravi worked on this dependent types of JavaScript, which was very cool stuff. But it's more complicated. I think Lindsay Cooper has this thing has a tweet somewhere where she says nothing scares verification people more than the following statement, X++. They just freak out. It's like, we don't like, that's really hard. And, there's some truth to that. Like incrementing a variable is just really hard. It's not as hard, it's surprisingly hard to track when you're doing kind of formal verification. So anyway, I guess there's just this kind of natural gravitational thing where like gradient descent, just working with functional languages. If you're working on a type system, it's just easier to work on this kind of stuff, right? So yeah, that's how that happened. But then I had a student, Panosh Vekris, who we essentially did a second iteration of the type.
Yeah, I tried to collaborate with Panosh for a while before I left.
Before you set off, and right, so he did this thing for TypeScript, which was it was a lot of fun because so TypeScript already did this thing where it's like JavaScript, but they've already given you a baseline level of typing, right? And this was TypeScript circa 2015-ish, 2016. It's amazing now. I love TypeScript. If we have some time, oh my God, it's 3:30 already, but I'll show you this site that we just built. Half of it is TypeScript. There's no checking really going on, but like 90% of the work was that. And the backend server is Haskell. But it was a lot of fun working with TypeScript. But then Panosh also graduated. He's off working at Facebook now on Flow. So, and then I guess Nikki was working on Liquid Haskell, and Eric Seidel was another of my students. Anyway, so they were working on Liquid Haskell, but Nikki's graduated now, but I like working on the code base enough that Nikki's also still working on it. So we both kind of work on it. There's other people who kind of contribute, that it's kind of easier for me to keep working on that. But I will say that what's happened, come 2020 is Rust is really big now. And all the difficulty we had working with these imperative languages, it's already factored into Rust. They did it. I mean, it's there, and people are working with those types anyway, right? With all this borrowing and aliasing. And so adding refinements on top of that is not that hard because really, so yeah, we may go back to the, stay tuned. There may be something there. We'll probably work on that.
Cool. Yeah, that's an awesome intro overview of your life and refinement types. Thanks, Ranjit.
Oh, you're welcome.
Yeah.
Yeah, you want to get into some demos?
Oh, sure. Yeah.
Yeah.
Let's see.
Yeah, I definitely want to see the TypeScript demo. That sounds pretty interesting.
No. There's no TypeScript demo. The demo is all Haskell. I regret to say. What I will show you is
Ah,
that
okay.
we built, that everything, the code you will, the system you will see that's running, it's running TypeScript. You will not see any TypeScript, and you will not see any types in the TypeScript. I could show you if you wanted.
Yeah.
I see. Okay.
Also, I forgot that Ranjit and I are actually like technically collaborators on something, which he may or may not demo.
If we have time, yeah. So Gene, this is a project that Gene got us started on many years ago, but it's finally a thing now, and you know.
Yeah, I'm really excited. It was like, yeah, I haven't seen it in a while, but I hear it's like really going well.
Cool. Yeah. So anyway, we get to that at the very end. Maybe I'll show you a few. I don't know. Maybe should we do some examples or something? How do I do this? I share my screen.
Yeah, you share your screen,
Yeah.
and then everyone will be able to see it.
Desktop 1. No, I don't want that desktop.
So-
I want desktop 2. Okay, very good. Share.
Yeah.
Yes. Sorry.
Yeah, I was going to say you can share your entire desktop, which you may not want to do, or you can share like a particular window. Either I think that looks good.
I find it too hard not to share the whole desktop. You know what I'm saying?
Yeah.
I'm just gonna
Yep.
thing. Keep it simple. Let's see. So here, okay. So I don't know what you all saw last time. I guess if there was like a bloop where you can just like fast forward me, feel free to do that.
Oh yeah, no, we didn't do any demos last time.
Oh,
So
good.
last
We
time we
didn't do-
just talked about like, what is this? It was
Okay,
very
so
abstract. So this is perfect.
So I'll show you what it's like to program with this stuff, right? So functional programming people always sort of go on about how they don't have, null dereferences or any kind of crashes, but that's not actually true. So for example, this is in Haskell or OCaml, you don't have a null dereference technically. You have the equivalent thing, which is what is called a pattern match failure. So here's how you might get a pattern match failure. You can write a function that returns the first element of a list, right? So you would say, okay, if a list looks like X followed by X's, then what I want to do is I want to return the first element X, okay? And this will be fine. So GHC or whatever the Haskell compiler, the OCaml compiler would mostly be okay with this. Except that now with so we just recently did this thing where Liquid Haskell is now kind of runs alongside the regular Haskell compiler, right? So can you see my screen? You should be able to see the giant red line. And what this red line is saying is like, look, this is all well and good, but what about the situation where this is kind of complicated? The error message is kind of involved. I see you wrote this function called head, but there's something I don't like about head, which is that you have not told me what to do for empty lists. Okay, so like, what are you going to do if the list is empty? And so here we have to kind of scratch our heads, and you might say, I don't know, if the list is empty, throw up a kind of error, right? Just say, oops, the list is empty, something like that, okay? And now if you do that, the little red line has changed because now, so this error function, what it does is it's a kind of built-in execution. It's a library function in Haskell where it says, look at the thing. It says stops execution and displays an error message. So this is only slightly better than a segfault. It's like a segfault with the string, oops, the list is empty, right? So what you really want to do is say, no, I do not. I want to make my program so that I want to be able to pull the first element out of a list, but I want to get a guarantee that I never ever call this head function with an empty list, okay? So here's what you do. With something like Liquid Haskell, you can essentially define what it means for a list to be empty or not empty. So I can say, I'm just commenting stuff out, right? So I can essentially define a type for say non-empty numbers. Okay, I would say here's what a refinement type is. It looks something like this. Okay, so what I would say is here, and I can uncomment it, right? So I can say, look, we all know what an integer is. Okay, that's just like a regular integer. What I'm going to say, I'm going to define a thing called nat, which is integers that are greater than 0. Okay, so far so good, right? This is just like non-negative integers. Then what I can do is I can write a function that tells you how many elements there are in a list. So for example, what I would say is here's here's a function. So it says here's a function called list size. It takes list as input and it returns an integer. And if the list is empty, then the size is 0, right? And if the list is non-empty, list size, if the list is non-empty, then the size is 1 plus whatever the size of x's is. Okay, so this is like a little recursive function that tells you how many elements there are inside a list. Okay. And now what you can do, coming back to our friend head, I can now write a refinement type that tells you what a non-empty list is. So I can say a non-empty list of A values or thing, to continue with my mass transit analogy. A non-empty list of things is simply a list of things, things, such that the size of that list is greater than or is strictly greater than 0, right? Oops, no need for an X. Okay. And now what you can do is you can essentially promise to only call head, not with any list. What do we call this thing again? Non-empty list.
Non-empty list.
I will only call head with non-empty lists. Oh, what is your problem? Non-empty list. What is the grumbling about one thing or the other? This is the trouble with doing demos like this. Did I screw this up? Head, la la la. What? Non-empty list of thing. What is it? Maybe we should look at the error message sometimes. Blah blah blah. Oh, correct. It says, I don't, okay, if you look at the thing, unbound symbol list size, what it says, I have no idea what list size is. And so now we sort of tell the checker, oh, here is a thing called list size. I will now, from now on, be talking about it. Okay. So please use that thing that I just defined called list size. And why is the checker not working properly? Now, what is your problem, pesky fellow? Oh, it's not numeric. Oh boy, what have we done? One should never do real life demos, should one? Sort is not numeric. Measure, list size. You know what? I'm just going to delete this. Oh, correct. Oh, this is the problem. It's not list size that is greater than 0. It's the size of the list itself that must be greater than 0. Excellent. Okay, so there was a little typo there. This, by the way, is why we have type checkers, to catch typos. Okay, here we go. So now I just define head as a non-empty list and so on, right? So let's look at another example. Can I do another example, Jean?
Yeah, absolutely.
Yeah.
Okay. Suppose I want to write a function that takes a list of numbers and computes their average. Okay, pretty straightforward, right? So I would say average takes a list of integers. And what does average do? If I have a list, I add up the elements in the list, and then I divide by whatever the size of that list, right? List, I divide by some n, right? And when Haskell, you can essentially say, whoops, n must be, whoops, oh God help us, must be the size of that list size of x's. Okay, so let's see what happens. Oh no, we get a little red squiggle, and what is the thing? It says, inferred type is that list I am a list size is not a subtype of the required type not equal to 0. And so the reason it wants this argument to be non-zero is, again, because here we're dividing, and we really don't want to divide by like 0, right? That would again be one of those pesky runtime crashes. And so now I'm getting an error. So maybe somebody can suggest, how can I fix, how can I change things in this definition of average so that I don't get this error? Like, is it legit to call average on all kinds of lists? Any suggestion?
Check the chat.
Let's head over to the chat.
Ask the chat.
In the
What
meantime, Ranjit, someone had a question for you. What's measure?
Yeah.
It's just a keyword.
I had the same question.
It's a measure is just like, it's a keyword. It says from now on, I will be, please allow me to talk about, so inside my types, please allow me to talk about this thing called list size. So measure is just for historical reasons. It's like, I am defining a thing called measure. Please, I'm defining a name, measure. Here is the definition below. Please use this definition inside. Please allow me to use this definition inside my type specifications, right?
Okay.
That's all I'm telling the system. Oh, okay, sure, I'll do that. And so there's certain restrictions on what kinds of things you can use inside the type specifications. For example, if I wrote some kind of BS function that just looped forever, that would not be well defined. So if I say list size, you must allow me to use list size inside the type specification, then it does some other checks on this particular definition that makes sure that it's okay to actually talk about list size, that it's actually a well-defined object. Otherwise, you could just be proving weird things. For example, I might just say list size of x's is equal to list size of x's, which is kind of a junk. It's like a meaningless definition. It would allow me to prove whatever I want, right? And so here, what I'm telling it is, here's a definition for list size. Please make sure it's kind of well-formed and it's kind of sensible. And once you have checked that it's well-formed, allow me to talk about it inside my types. And that's what measure is saying. Okay. So returning to average, do we have any hypotheses on how we might modify the signature of average?
Yeah, we have a
I
few
think
in the chat.
exactly. Pierce hates speeches has got it right. Could specify that average only applies to non-empty lists, or I saw in either Pierce. What is the or? Oh, scratch the either, eh? But you can have a case if the list is non-empty, use this. Otherwise, use zero. Fantastic. Oh my God, look at that fractal. Oh, cool. Okay. So you can do either of those, right? So you can either, let's do Pierce's first thing, right? Average does not take any list. It takes, what did we call them again? Non-empty list,
Non-empty list.
int, and whatever produces an int. And that'll make the error go away. So notice the little red squiggle is gone. Or this is the other suggestion, right? So this is, this, what is it? Postel's law, right? Be permissive in what you what is it? Be permissive in what you accept, but conservative in what you sort of return, right? So this is being very restrictive. It says, no, please don't call me with things that are not empty lists. Otherwise, I will yell at you. Or what you can do is you can do what the other suggestion is. We can test, hey, is this list non-empty? So for example, I would check, hey, is that n greater than 0? If so, let's do some whatever this. Or, otherwise, if the list is actually empty, right? I might now just return, I don't know, what should I return? Like 0 or something, right? Which is kind of a terrible thing to do. Instead, so in Haskell, this is just, it's out of an OCD thing. In Haskell, you're not supposed to return 0 as the average of an empty list. You could, if you like. If I was like going back to my C roots, I would call this like -1 as the average, which I guess is even more silly. The kind of, the way you're supposed to do this is with a kind of maybe null value, right? Where you say, in this case, okay, I return just, think of it as a non-null, definitely not null. So now this is complaining because it says that the output type is an integer. It's not actually an integer. It's maybe an integer, okay? And so notice the important thing over here is that we're checking that n is greater than 0. If we did not do this test, then this would fail. For example, if I just made this, I don't know, if I make this n greater than equals to 0, then I get an error over there. We'll say, no, that's not good enough. You might end up, if n is equal to 0, then you're back to square one, right? So what's the point of that? So here we do this test. So anyway, those are two possible ways in which you might fix it. And if I have time, I might do one third demo to just continue this, and then we can stop. Am I allowed to do a third demo, G?
Yeah, absolutely, please.
Yeah,
okay.
sounds great.
Let's just write this. Here's a fun little function. Okay, so my 6-year-old she just finished reading, whatever, she's 7. So she's been reading the Harry Potter book. So Slytherin, I assume everyone knows what Slytherin is. It's one of whatever, it's like the bad guys, right? So I wanted to write a function called unstutter that takes a word like this, lots of Y's and so on, and removes all the duplicates, okay, to just Slytherin, something like that, okay? And so the way I might do this, let's just use this head. So here's how I would write such a function. So check it out. I would write a function called unstutter. And the idea, here's the strategy, right? So in Haskell, something like this, I'll pick a smaller list, like maybe just with CCCAAATTT, something like that. Imagine I had a string like this. In Haskell, the default way strings are represented is as a list of characters. So this is actually list of C, C, C. Oh God, I'll just make it 2 C's, 1 A, and like 4 T's. Okay, T, 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 like so. Okay. So the way I'm going to implement this unstutter function is I'll take this whole list and I'll chop it up. I'll write a little function called group that essentially clumps these. So it's going to return as output the following list of lists. Okay, so it'll return a list. Oh, hang on. I'll just copy this. Whoop, like so. Oh, man. C, okay, and then a list with just A, and then a list with 3 T's. Get it? Okay. And then once I have that, I'll just take the first element from each of these lists. Okay. And so that's going to give me back my unstuttered version, which is CAT. CAT. So far, so good? Okay, cool. So let's see how the strategy works out. So what I'm going to do is I write a function called unstutter. It takes a list of A's as long as I can do the equality operation on those A's. That's what this means for those not familiar with Haskell. Think of it as A implements equality if you were a Java programmer, and gives you back a list of A's where these duplicates have been returned, right? And what this does is it calls this little function called group. And here's what group does. So I'll just show you the implementation of group. Group is going to take, again, is going to take a list of A's, and it's going to give you back now a list of these blocks. That's a list of lists of A's. Okay, this is the first set of C's, then a block containing the list with A's, then the list with T's. Okay, and what is group going to do? Well, if you give it the empty list, you get back the empty list of blocks. If instead you give it some list that looks like this, X followed by some X's, then here's what we're going to do. Okay, I'm going to return, let me think about this. I've forgotten this. It's going to be something like X const EQX's and then rest where, let's look at what EQX's does, right? EQX's and rest are going to be, oh man, I should have just, right. Oh, I'm trying to think. Oh boy, I should have remembered this off the top of my head. So what I'm going to do is a function called span, which essentially collects all the elements that are equal to X. Okay, so it says, give me, let's pull out all those fellows Y that are equal to X and run it on the list X's. So it's going to split. So what this is doing is splitting it into, these are all the fellows that are equal to X's, and this is everybody else. Okay, and I'm going to then put X together with all his friends that are equal to him. And then I will recursively call group, something like that. Okay. Oh boy, lots of errors. Span, termination error. Oh no, termination error. That's no good. Hang on. I'm going to cheat a little bit. And I'm going to look at my actual solution for this, which I have squirreled away somewhere. Yeah, it wasn't so bad. Here. If you're wondering how I could possibly have written this so fast, here's how. Through the magic of copy and paste, like Julia Child pulling a roast chicken out of the oven. Okay, here we go. So here's my group function. That works just fine. But my unstutter now is complaining. It says blah, 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 is not a subtype of the list size greater than 0. Why? Because look at this. We're calling head. And how do I know that this call to head won't crash? So can somebody tell me what is going on with group? There's something magical that group does, which is that each of these lists is in fact not empty. Right? And so once again, here's a kind of way you would want to use group, but you would say that group is actually not quite so silly. It takes a list of A's and it gives you back a list of non-empty things. And once you do that, the type error goes away. Okay. And you can, in fact, now, we should actually try running code sometimes. Let's see if this works. Unstutter, check it out. Okay. So I just ran it and it actually gives me back what I want. Does that make sense? So here, all I did was you tweak the type system. So this is, I think, one of those classic examples where I was talking about, if we tried to do this in BLAST land, it would be impossible because, there's all this information. I took it, I created a collection. I'm only creating non-empty collections, trying to figure this out purely using the kind of machinery we were using with program logic and model checking was essentially impossible. But here it's this happy marriage of type systems, which right now, to me, it feels very natural where you just say, oh, don't worry, it's a list of things, but each of those things is itself a non-empty list. And that's it. And everything else, all the pieces just sort of snap together nicely and give you what you want. Oh boy, I'm going to stop talking now.
How does that work with, sorry, I had a quick question. And there are also some requests in the chat as well for demos. How does this work with so I think you also define group, an empty, if you call group on the empty list, it returns an empty list.
Oh, see, so, that's right. So if you look at the type, what it says is I'm a list of things. Each thing inside me, I'm a collection. So think of this box as saying I'm a collection. Okay.
Yeah.
I'm a collection of things where each of those things is itself a non-empty list. So the collection might be empty, which is what would happen if you give me an empty list to start with. You get back as output a collection that is itself empty. That's fine. All I'm saying is when I ever put anything inside that collection, that thing is going to be non-empty.
I see. I see.
So for example, here, let me, this is actually much easier to show you like this. So here's a simple example. EX1, I'm going to say EX1 is a non-empty list of integers. Okay. I have to put it inside this pesky quotes. Sorry. And EX1 is, okay. So for example, EX1 equals 1, 2, 3, 4, 1, 2, 3, comma, 4, 5, 3, 4, 5, comma, whatever, 5, right? So this is fine because each thing in my collection is non-empty, right? But, and so of course I can delete all of them and that's all good. This is still non-empty. Right. But if I went inside this 5 and I commented that out, then bad things would happen. You'd be like, oh, wait a minute, that's not legit. Get it?
Yep.
So sorry, just for CD, I want to get read.
Well, so Ranjit, there are a bunch of questions in the chat, and there are a couple of demo requests. One is for like list length arithmetic. One is a question about Liquid Haskell and I/O. If you want to do the web framework, Ranjit, like I think that would be really cool because like that might like also cover the I/O question. I don't know.
It does. Oh man, this fractal. Let's see. I mean, we have, so I can jump and do any of those. Which, do you have any preference, Jean? How do you want to do it?
Well, I'm biased, but I think using Liquid Haskell across the web framework is nuts. I think something that we talked a lot about last week that we didn't talk very much about this week is the decidability of Liquid Haskell. So like, I believe the decidability is core to the usability of it because you don't want your type checker to hang. It's also like the way you guys have set it up is brilliant because you can do all this stuff decidably. But then I think the fact that you can actually verify Liquid Haskell properties across an application code and database code, like in a decidable logic, is totally nuts.
It's pretty cool,
and so that's why I think like the web framework stuff from my perspective is super cool.
Let's see. Yeah. So let's see. Maybe I'll just take a quick look and see if I can answer things. And then here he excluded head from the prelude top, missed that locally defined. Yes, that was a locally defined head, by the way, because I just wrote it myself. I wanted to kind of begin at the beginning. Was there something about arithmetic? How does head know?
Yeah, someone wanted like list length in the types and adding them in a demo.
Oh, adding list lengths. Oh, that's an interesting example. I could, yeah, sure. Like, let's try and do this. But it's a bit of a rat hole, but okay, we'll just do it quickly. I promise, okay, I promise after this, Gene, we'll switch to the web thing, okay? Because like, who cares about lists anyway? Actually, I do, but we'll switch to something more realistic in like 30 seconds, okay? So here, let's just do a quick one. So the super boring hello world example is when you take two lists and you append them and you want to say the list sizes are added up, okay? Let's do something slightly different. So I'm going to reverse a list. This is just slightly more interesting. It's kind of just mildly more interesting than, so I'm going to write a function called reverse or rev. And what rev does is, if you give it it reverses the list, by the way, rev for reverse. So if the list is empty, it just returns this, okay? And if the list is non-empty, you return something like, you essentially reverse x's, and then you stick x at the end. Okay, so this is kind of this is the first way to do it, but some people might say this is the noob way to do it. And it's the noob way to do it because this is a really slow operation. So this is not like a linear time operation. You kind of have to go, oh, what does the comment say? Oh, the first list is not finite. Anyway, never mind. So now the faster way to do it is something like this, right? Is you write, so when I teach my kind of functional programming undergrad class, you write a little helper. Oops, sorry, a helper, which essentially works like this, okay? It has this kind of accumulated, think of it as a stack, which is gathering the list backwards. And when the list is empty, you just return the stack, okay? And when the list is, oops, sorry, helper stack is not empty, okay? What you do is you recursively call the helper after you push X on top of the stack. Oops, sorry, stack, and then you recurse on X's. Okay, so now what this rev helper is doing is it takes a list and another list and gives you back a list. Okay, so far so good. Now there's some grumbling about what is your problem. All right, that this is not even a valid Haskell. You need an equals over there. Okay, good. So all of this type checks, this is great. But now suppose I want to say that the list that I gave you, suppose I give you some input list X's. What I want to say is that the output list has the same list size, okay, as the input list. Right? This might be a thing I want to say. And oh, by the way, I want to rewrite this. So now I'm going to rewrite, oh, sorry. I don't want to use this noob version of reverse. I want to write a slightly cleverer reverse that when it takes a list X's, it calls my helper, whoops, sorry, starting with the empty stack. Okay, makes sense? But now the checker is complaining, it's like, no, I don't believe that the output list is the same as the input list. And the reason for that is if you think about what this rev helper is doing, it essentially takes this stack and it keeps peeling off the elements one by one from this and adding them there, right? And so the output list in this case, the length that it's going to have is going to be the sum of the lengths of these two input lists. And so now if I tell my type checker that, it's like, oh, no need to freak out, my friend. Here's how rev helper works. It takes as input a list called x's and another list called y's, and it returns as output a list such that list size of out equals list size of x's plus list size of y's. Then with any luck, this will type check. I should say any luck because I haven't tried it anytime recently. There you go. Okay, so now it's happy. It's like, oh, okay. Since these two things add up, it knows that the size of this list is 0. And so 0 plus whatever x's is going to be the same as x's. You see what's going on? So here's a quick example where we did some kind of arithmetic on the sizes of the list. And by the way, let's just, writing types is all well and good, but you really should run your code. So let's just make sure this works. 1, 2, 3, 4, 5. Let's just see if it actually runs. Oh God. No, I mean this rev, you pesky fellow. What is your problem? Sometimes, there we go. 5, 4, 3, 2, 1. So it in fact does reverse the list. So we have a little more confidence. Is that good? I don't know who asked that particular question about arithmetic, but hopefully that works. There was a spot of arithmetic. Okay, let me show you the thing that Gene is excited about. And I confess I'm also excited about. And really Gene got me into it. So, Gene has double reason to be excited about it. It will require that I go off into my browser. So check it out. Here's a little web page. This is all TypeScript running on a server somewhere. Please sign in. So I'll just show you what the website is, and then I'll show you where Liquid Haskell comes in. Okay. So it's a website I wrote called Voltron that uses Binah, by the way. Binah is this framework. So if I sign in, here's what happens in Voltron. So I lecture, right? I'm a professor, and I wanted to do exercises, in-class programming exercises, whatever, right? I give them little things to write. And I wanted to see what the students were writing as part of their solution. So I was like, let me build a little website where as the instructor, I can create groups. I can put students in groups, and each group gets its own little buffer like this, right? This is just like a scratch pad. So they can just, it's like an editor buffer. I can write stuff over here, okay? Write stuff, whatever, right? Here's another buffer, hello, okay? And so in real time, as the students are writing this, I get to see it, but I get to see all their things. And the students, of course, just get to see their own view. So as the instructor, I can kind of switch out. Oh, I also have a secret account as a student with that hello thing. So see, I get to see this buffer, right? And I can go back in here. I am a student. Okay. And now I can pop back to my instructor mode, and I'm going to get to see all this. Okay. So this is the website. It's pretty fun, but it's like a little web app. There's students, there's like an authentication, there's logging in, logging out, and so on and so forth. So in order to make this work, the way it's implemented is we wrote this is like, it's all Gene's fault, by the way. Okay, so we wrote like a web framework, which you can think of as like Django or Ruby on Rails, or that kind of thing, but in Haskell. And the cool thing about this web framework is that, like in every web framework, there's a kind of database-backed application, right? So there's a whole bunch of different kind of database entities. Like there's a user. So here's this is what you would just write in any of these frameworks. Ruby on Rails, this is like an active record or something, right? A user has an email address and a password and a first name, and they can set their language theme. And there's a notion of a class where there's university and the name of the class and who the instructor is. And each class has a collection of groups. There's an editor, blah, blah, blah. I enroll students inside groups. You don't have to really pay attention. For example, when I need to reset the password, there's this little reset object and so on and so forth, right? So now the cool thing that we did with Binah, and Gene sort of tricked us into doing all of this, is that we can now write cool policies. So for example, this policy says you can write all manner of policies that say, for example, the only person who's allowed to read the password is the user themselves, or nobody is allowed to change the email address or the authentication level of a particular user, right? Or what this says, as you can see, update. So you can, the first name and last name can only be updated by the viewer themselves. So the person logged in has to be, you can't change, I can't change Gene's first name or last name, right? Things like that. So, and the nice thing is you write these policies and then they get checked at compile time, right? Everything gets checked at compile time. So for example, I might go to this reset password thing, right? And I only want to allow you to reset your password if the code that you have, like just now, I had to do this in Twitch, right? To log into Twitch, they sent me an email, a unique code, and I had to enter the code. And I want to specify in my policy that you should only allow people to update, update their, update uh, their information, right? Or update their passwords, if in fact if they had a valid code. So you would write a little policy that looks like this. You can only update your password if the code that you sent in was valid. And where valid is defined as, much like list size greater than 0. It's a little predicate like that. Somewhere over here, there's a notion of when a code is valid. So for example, if this valid condition is true, then this code is valid, right? So now when I add that particular policy, what's going to happen is I sort of come back here and the type checker grinds away. Here's a bunch of, here's my code that was actually checking whether or not I was, correctly checking the validation codes, right? And now notice, whoop, I get a compile time error. I changed the policy and said, oh no, please make sure that I check that the password is valid, the reset code is valid. And now I get this error over here. It says, no, 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 look, you are updating the password, but you have not checked if the user code is valid. Okay, so all this happens at compile time. And what happened is, in this case, in the place where I was checking if the reset code was valid, I forgot to check that the valid bit was actually true. So if I go back over here, I now sort of add that, oh yes, there was this check that the in the database record that the password valid field was actually set to true. When I do that, now the type checker is going to be like, oh, okay, in that case, you've sort of verified your policy, right? And there are various kinds of cool little policies that you can specify. One of my favorite ones is, this will eventually come back. I don't know why this browser is, the editor is taking a little longer, but look, it's sort of gone, right? Here's another example. I think you should only be allowed to have, so this particular, I'm just going to delete it, right? So we have a policy that says that the only people who are allowed to have access to a particular group's buffer. So here's an editor link, right? The only people who are allowed to have access to a group's buffer is if you are the instructor of the class, or if you are a student who has been enrolled in that particular group in the class, right? And so here, for example, in your code, if you forget to do that particular check, that this particular check that I deleted checks that you are in fact enrolled in that particular group, in that particular class. If you forget to do that, then you get a compile time type error. It says, no, 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 you might be sending this buffer to somebody who's not in that group. And so when I put that particular check back in, and now when I recompile, it'll say, oh, good, you have now satisfied all your different security policies, right? So the cool thing about Binah is that you get to write these policies in this one place. Who's allowed to read this? Who's allowed to write that? Who's allowed to update it? And then Liquid Haskell essentially does its type checking. It's not checking list lengths or whatever. It's checking these far more interesting kind of security policies. But I will stop talking there and let, I hope that's fun. I hope
this is amazing, Ranjit. You've done like so much with
Yeah.
this. There are a bunch of questions in the chat that I guess we've passed the end of the hour. So I'll try to wrap up very quickly with a couple of questions, and then maybe Ranjit, you could address some of it. There's many, many questions. Everyone wants to know so many things about you. So maybe if you have time, you can chat back to some of these people. But there are some questions about Binah, which is like, is it supported by all features that exist in Liquid Haskell right now? I think one question I had was when Jordan and I had left it off, we got stuck because we reached the edge of Liquid Haskell capabilities. And there was one more thing we wanted, which was the ability to talk about the row itself that we were writing the policy on. But even as of then, like something I want to point out to the audience is it's really freaking cool that you can use Liquid Haskell to do verification in a decidable way across the application code and database code. Like something that Ranjit helped us figure out was how to model database queries and like unroll them decidably, which is nuts. And then it seems like after that, Liquid Haskell got extended or something. So I don't really know what happened, but it's amazing now. Like we definitely didn't have all this stuff when Jordan graduated.
I'll tell you exactly what happened is we had this absolutely brilliant student, Rose Kunkel, who joined, and Rose just figured out how to do all these. It turned out we didn't have to change Liquid Haskell. It was just that Rose, so there's this paper that we wrote at ICFP 2015 called Bounded Refinement Types, which is a very cool paper, but it's very complicated to actually use that stuff. So, there was like one person on the planet who really knew how to write that stuff, who knew how to work with those kinds of type signatures, which was Nikki. But then Rose essentially figured all this, like, oh, why don't we just use this stuff? And then Rose essentially figured out how to build this kind of typed API for interacting with the databases. So what is happening in the, I sort of removed the browser windows. What was happening in those little queries, all those things that I was deleting and so on, we were just building up database queries. And all of those little operators, the equals with a dot and the and, those are all actually very clever types that Rose figured out how you can
That's
write
amazing.
database operators where everything just works.
How did you guys do like referencing the row itself? That was like where I think Nadia thought we needed to do some extension.
So that was another very clever thing that I think, I forget, it was Rose or I have another really good student right now, Nico. Between the two of them, they, so I mean, that would get very technical. I don't know.
Okay, yeah, we don't have to go into it.
But we did figure it out, and it's beautiful because now we can kind of talk across.
Yeah, that's incredible.
And that was
yeah, no, I thought like one of my hopes for Liquid Haskell was if you can actually use it to verify these real world programs, and like you can plug it in with your refinement type JavaScript, you can like type your web program all the way through, and I was really excited about that.
That would be very sweet.
Yeah. That'd be really, really exciting. Cool. So we are past the end of the hour, so we do have to wrap up. Ranjit, there are many questions for you. You can either choose to answer them in the chat or not.
No, I'm happy to answer them. I mean, what is the protocol here? Do we like pull the plug, or does the chat, is it like
so the chat is still there if we turn off. So like what some people have done is just like sit there and hang out in the chat for like 5 to 15 minutes after. Yeah, that seems best. Because a lot of people end up having to go, so we try to end the video like on time.
Okay, that sounds good to me. So I can just stick around and just like answer the questions on the chat. I guess it's, so I don't know if you have like an explicit, this is it, everybody.
Yeah, cool. Well, so I guess we'll tell everybody about what's coming up. Yeah, follow Ranjit on Twitter. We'll link his Twitter account. His Twitter is great. Ranjit is the best. He obviously he's very famous, but I think he's still underrated. So tell everybody about him. But yeah, so next week we have Nate Foster, who's a professor at Cornell. He's coming to talk about network plane verification with P4 and Prev4. And then the week after, we have James Wilcox, who was a PhD student at UW. He is currently the CTO of a blockchain verification company, I believe. But he's going to come demo Daphne, which is one of my favorite verification frameworks. It's like your favorite object-oriented language plus preconditions and postconditions. Love those, love that for logic. Yeah, so let's thank Ranjit, everybody, for coming today.
Thanks for having me, Jean and Hongi. This was fun.
Yeah, thank you. This was
thanks, Ranjit.
this was really
this is awesome.
Cool. Yeah, thanks, Ranjit, and we will see you in the chat.
Okay.
Yeah.
Bye, everyone.
Bye, everybody.
Bye.
You can tell me when it's over, if the degree is worth the pain.